recording, so you don't have a prompt pop up on your screens. Hope you've all had a good weekend. What we're doing today, just to remind people, because it's a couple of weeks since we did our last call, and you may remember on the last call that Jim Reed mentioned the presentation that he'd found most interesting at the recent RIPE event last month, which he thought would be very relevant given we were discussing encrypted SNI or Echo, the most recent iteration of it for those of you that are on the call, and pointed me in the direction of Luca Deri, who has kindly agreed to join us today. So what we're going to focus on today, Luca will sort of give a presentation. I've sort of allowed plenty of time for a discussion and Q&A when Luca has gone through his slides, and hopefully we'll be able to do it a bit more justice, Luca, than the time you had at RIPE, which I think was only 10 or 15 minutes in total, which is rather quick, to say the least. So that's the plan. So what I'll do in a moment, I'll just pop Luca's slides up on the screen so you can all see them. But before we do that, might be worth, sorry, it's my phone ringing, I do apologise. It might be worth, Luca, would you mind introducing yourself properly in terms of your background and also ntop, just for those people that haven't come across it before, so they got some context, and then I'll put the slides up, if that's okay.
Yes, sure. I prepare one slide, so if you want, I can.
Oh, okay. In that case, let me put that on the screen then.
So you are running the presentation?
Yes, if you've got a slide, I'll put it on there for you if that's on the slide.
So I can share my screen if you want.
That should be on there now, hopefully.
Okay.
Can you see that? Is the slide on the screen?
Yeah. Okay, so we move to the next slide.
Yeah, surely.
Okay, the one after, please. Slide number 3.
Ah, yeah.
So just to give you a short introduction, my name is Luca Deri, and I founded this company ntop, about 20 years ago. We are developing open source software, mostly for network security and traffic monitoring. The idea is that we want to create an infrastructure that is open source, that allows people to monitor the traffic while be open, to extension. This means that we are able to ingest traffic coming from various sources, not just in form of packet, but also in format of flows and similar things such as NetFlow, IPFix, JFlow, and SFlow. And over the years, we have developed various tools. And today I'm going to talk about nDPI. That is a deep packet inspection toolkit that we have designed about 8 years ago. And that is the focus of this presentation. I'm part of the Intel Innovator software. I'm based in Italy, in Pisa. And I contributed to various open source software, not just those I've developed, such as Wireshark or others. And so this is my background. So network security and network traffic monitoring and open source software development. Okay, we can go to the next slide, please.
Yep.
So in essence, the idea today is to talk about the requirements for analyzing network traffic, so for monitoring traffic. And many people need to do that for various reasons. There is not just one reason, but there are many of them. And so sometimes, people want to limit the bandwidth of specific protocols. So here I mentioned BitTorrent, but you can imagine many other protocols. So for instance, today people have problem with, the uplink. So they want to reduce the uplink of some protocols, such as Google Drive, for instance, for uploading files. Other cases include the ability of spotting and stopping malicious communications on encrypted channels. So let's say VPNs that are not allowed, or protocols such as Tor, the Onion Ring, things like that, or to prioritize traffic protocols such as Zoom, for instance, today. So we want to make sure that the video conference is smooth. So therefore, it is very important that those protocols, are working properly. Over the years, traffic encryption is becoming pervasive, and some people sometimes say, okay, this is not a big problem because we can decrypt it. We can inject certificate authorities, that allows us to decrypt it. But this is not a good option. First of all, because it violates the user's privacy, so it's bad. But in general, because this is not a solution that you can apply everywhere. For instance, there are some protocols such as TLS where this can work. But there are other situations where you cannot inject any protocol, or that the user can somehow see that there is something, there is somebody in the middle. So therefore, it is not a good idea. And also because the traffic will become encrypted more and more, and therefore it is a good point from a point of view to start dealing with this change, and to make sure that our software is able to understand what is going on. Okay, please move to the next slide. So in essence, the idea today is to present you, some techniques that allow people to understand and to fingerprint encrypted traffic. Fingerprint means to find a way to somehow characterize the traffic and to recognize it over time. So for instance, we can use the certificate, or we can use other characteristics of the traffic so that we can detect it in the wild. So it means that, for instance, if you have, let's say, a malware, okay, that is running on some of your PCs. So if I'm able to find a certain fingerprint of this traffic, regardless of the IP address, for instance, I can identify the traffic. And also, we want to make sure that there are the communications that are flowing in our network are only those that are allowed. We don't want to allow people to run communications that are not safe, or that violate our policy. And also, we want to make sure that we can, while not be able to expect the content, but we can monitor the nature of HTTPS communication. So for instance, the typical question is this real HTTPS? So are people exchanging web information, or is this HTTPS-based VPN? So these are the typical questions. And also, to identify malware is it's a big thing, especially in companies or in network operators, where a malware can be a problem, not just for some customers, but can create a lot of traffic that can put a lot of pressure on the network. So it is very important to identify that. Okay, next slide, please. So in 2012, we have decided to create our own deep packet inspection toolkit. The reason was that we were somehow aware that there are products available on the market that are able to do that. But the problem with those products is that many times they are, if not all the time, they are proprietary. So if you want to add a protocol, you have to speak with the manufacturer, and they are designed for various purposes. So sometimes they are designed, let's say, for doing things like lawful interception, because sometimes you have to comply with the law. This was not our idea. So our goal was to characterize the traffic, to do limited metadata extraction, where metadata means that we want to extract some information that is useful for our purposes, for characterizing the traffic. We don't want to spy people or do anything more than that. And we believe that open source has a value in this, because people is able to identify and read the code. And in particular, it is able to operate nDPI locally without any cloud support. So it means that we are able to detect the traffic locally on the machine where nDPI is working, without having to send any traffic to the cloud. So somehow violating also the country boundaries or other type of constraints. At the moment, we have about 140 protocols. When I say a protocol, I don't mean an IETF or RFC protocol, but we call protocol, for instance, things like WhatsApp, Telegram, or Zoom. Some people might say that this number is low, but for us, makes sense, because we have realized that people usually per host tend to use about 10, 15, 20 protocols at most. When we see many more protocols, they are not really in use, so probably they are probing attempts. Or we see that enlarging the number of protocols can create also problems, because when you have to set a policy on your network saying, okay, block peer-to-peer, okay, it's very hard for a network operator, network administrator to remember all the peer-to-peer protocols supported. So that's why in nDPI we have clustered protocols into categories. So for instance, peer-to-peer is one of those that makes things simple. And also nDPI is extensible at runtime. So it means that if you want to grow from 200 protocols to 2000 or even more protocol, you simply take a long list of domain names like many other competitors are doing. And let's say you define CNN as a protocol, all the traffic going to CNN.com, regardless of the exact host name that is accessed. So the idea of nDPI is to be simple and to be useful for network visibility. We don't want to compete in terms of number of protocols supported, but we want to make sure that all the modern protocols are supported. All the most used protocols, both in standard internet and mobile network, are supported. That's why we have the Zoom, for instance, or Teams, or this type of protocols. Next slide, please. Okay, so in nDPI, a protocol is defined as major and minor. So where we have, major is the transport protocol. So let's say QUIC in this case, or DNS. And the minor protocol or application protocol is the name of the protocol as defined in nDPI. So for instance, in this case, is YouTube upload. So it means that somebody is uploading a video on YouTube using QUIC. QUIC is the protocol. Like I've said before, don't take the word protocol, literally, but they are just used in nDPI terminology. And like I've said, in our case, the nDPI is extensible. It is extensible both coding a new dissector in C, or by providing a configuration file by you define your own protocol. And in nDPI, a protocol is defined as a label with a number and a label, and with some characteristics. So let's say traffic on port whatever, or traffic going towards host X, or let's say traffic that contains this SNI, or that resolves this host name. So this is the way protocols are defined in nDPI. Next slide, please. So this is an example, okay? So let's have a look at Netflix. Netflix, as defined in nDPI, is a protocol, but practically the Netflix protocol does not exist because Netflix is just a simple protocol for speaking with the Netflix network, but everything else is TLS. So in this case, as you can see, we have traffic going towards Netflix.com and NFLXT.com, blah blah blah, is Netflix. So this is the way it is defined inside nDPI. And we can do the same for other protocols. So this is defined at runtime. You can even replace the definition of the protocols while the application is run. So you can change, or you can extend the list of protocols simply replacing this file at runtime. Next slide, please. So in essence, traffic classifications was in a very simple way. So based on the traffic type, okay, so we define dissector, so it can be for UDP or TCP. And when we see the first packet of a certain flow, we start decoding the traffic based on the probability of success. So let's say if we see traffic for TCP port 80, nDPI starts checking if it's HTTP. If it is not, it starts with all the other dissector that can match this traffic. And in case we find that a certain dissector is unable to match a traffic, this dissector is discarded for this specific flow. So it means that after a few iterations, we are able to identify the real traffic, or we have to say unknown. So in case nDPI has not been able to identify the protocol behind it. And it is very important to say that for most protocols, nDPI is very precise, so it is going to dissect everything. Whereas for other protocols, such as WhatsApp, for instance, there are some heuristics, because unfortunately those protocols are a little bit, let's say, changing over time. And also because big companies such as Facebook, for instance, are using the same protocol for various purposes. So for instance, if you have WhatsApp or if you have Instagram or Facebook, the chat that you see, so when you send a message to another person inside the WhatsApp, is the same service. So from the network standpoint, it's exactly the same protocol. But in the case of Instagram, so it is used inside Instagram. In the case of WhatsApp, it's used to send messages. So these are the type of heuristics that nDPI is doing. So if you have, let's say, only WhatsApp running, it's simple. But if you're continuously switching from Instagram to WhatsApp and back to Facebook, then it's hard to say if this chat belongs to the Facebook app or to the Instagram application. Okay, next slide, please. Please interrupt me if you have questions. Just to give you an idea of the performance, okay, this is a slide taken using a pickup file captured from a real network with many protocols, and this is real traffic, therefore. So as you can see, packets are not that small. So we're talking about 10 gigabit of traffic, about 1.8 million packets per second. And this performance of classification has been achieved on a single core using an Intel E3 CPU. The reason why it is fast is because, in essence, in nDPI, we analyze the first few packets of the communication. We don't have to go through every single packet of the communication. Like I said, for UDP, mostly we need one packet, two maybe. For TCP, we need a little bit more, especially for TLS, if we have to read the whole TLS handshake. But in general, we inspect only the first few packets. So therefore, the load of nDPI is not that high, even though we have to do deep packet inspection, so to analyze the payload and to rebuild the payload in case of, let's say, retransmissions or things like that. Next slide, please. Okay, this was an introduction to nDPI. Because today you want to focus on encrypted traffic analysis, I have prepared another set of slides where I will be talking about this topic that seems to be interesting for this webinar. Okay, please next slide. So this is an example. So nDPI is a library, okay? So you can use it in various applications. So to make an example, many OpenWRT routers include nDPI to block through the Linux firewall network traffic, or there are many companies that are using it inside their own products. And nDPI, first of all, for testing purposes, but also for studying, because there are some people that are doing research based on it, also comes with an application called nDPI Reader that allows you to read a pickup file, a set of pickup file, and to extract some information. This is one example. So this is an Instagram flow. As you can see, nDPI is reporting two things. First of all, the fingerprint, and second, the behavior. In the fingerprint, nDPI returns information, let's say, about the client. So in this case, the SNI is decoded, or other type of fingerprints such as the JA3, so J3C and S defined by Salesforce. I will be talking about that in a second. Or for instance, the cipher being used to encrypt the traffic, and as well the TLS version. For behavior, it returns some information. This is just a subset of what you can do. So for instance, the byte distribution, so the standard deviation. So these are good, in particular, if you want to understand how traffic is sent over time, or if, let's say, it's a predominant send or predominant receive, or send and receive. And this is good, for instance, if you have HTTPS and you want to understand, let's say, if this HTTPS communication is used for HTTP, so you send a request and you receive a response, or if you send and receive, so it looks like, let's say, a VPN. Then it reports, information about the protocol. So in this case, TLS Instagram. So it's Instagram communication over TLS. The category. So in this case, it's social network. So like I've said before, you can classify traffic also based on the category. Information about the number of packets and flows, and the output. So this is very important for malware. If you have very long communications that are more or less not exchanging much. And then other things that are on the HTTPI, so for instance, ARPN, that says under TLS, I would like to exchange the traffic based on, let's say, HTTP 1.1 or the supported TLS versions. And then we have other things like, such as the byte ratio that says, you know, what is this flow out, so in this case it's download, or the inter-arrival time. And these are good for understanding the behavior of the communication. I will show that in a second. Can you please move to the next slide? Okay, let's talk about the fingerprint before we move to the behavior. This is JA3. JA3 is similar to HASSH, that is the equivalent for SSH, defined by Salesforce. So in essence, it fingerprints the client application, the client and the server, so that we can identify based on the protocol, on the options and extension used in the TLS echo. We can fingerprint the client and the server. So it is good for understanding, for instance, the type of client and the type of server, but it is not good for identifying exactly a certain client, because clients that are similar, or let's say if you start the same application, so exact the same version of, let's say, Google Chrome on 2 different PCs, then we have the same JA3 signature. Next slide, please. This because JA3, based on the options on the client and server hello, allows you to identify, in essence, the library. So in this case, OpenSSL. It is not identifying one application. So let's say if you have a Firefox or Tor or another application, Skype, let's say using the same OpenSSL version, okay, we can say they all have the same fingerprint. So JA3 is good for understanding delta. So let's say if you have one device, for example, one IoT device or one PC, and you start observing a different JA3 version than those you have expected or you have observed in the past. So either you have updated the machine, or somebody has installed some new software, or has updated the existing software. This is good for that. But if you want to use JA3 for figuring out whether there are certain applications, so let's say Firefox, or instead of let's say Chrome, this is not a good idea, because the way it works basically identifies the library, and this is the reason why it will lead false positive if you want to use it that way. Next slide, please. While JA3 is compatible with 1.3, unfortunately, other type of fingerprints, such as the certificate fingerprint, are not compatible, because in TLS 1.3, that is the latest version used today, the certificate is encrypted. So let's say up to 1.2, that is currently the most used version on the internet, it is possible to understand, let's say, and read the certificate. So to read the serial number, to understand if the certificate is too old, or to understand if the certificate is strong enough, it has been encrypted properly, or if it's an old certificate. Unfortunately, this information is not available in 1.3. So in 1.3, we cannot make this type of analysis. So we can only observe, when a client is speaking with a certain server, but we cannot understand or fingerprint the certificate. Next slide, please. So this is one example. So looking at the fingerprint, again, similar to JA3, we are able to see if the certificate has been replaced. But this is very important, for instance, for a web server or for an IoT device. So to see whether something has changed with JA3 in the software configuration, with the certificate fingerprint on the configuration of the web server, because somebody has replaced the certificate. Nothing more than that. But unfortunately, this feature is not available in 1.3. Next slide. So if you want to catch malware with fingerprint, it's probably not a good idea, because there are many open source IDSs such as Zik, the former Bro, or Suricata that are using that. But unfortunately, because of the nature of JA3, you have many false positives, because JA3 is identifying the library. So there are websites such as abuse.ch, for instance, that are providing you a list of potentially malware fingerprints, but don't take them 100% for sure, because like I said, they identify the library. So therefore they are good indicators. Okay, so if you want to put them in a bigger system, but you cannot drop traffic in your network based on those fingerprints, simply because they are unreliable. Next slide, please. So we need to do something more. So another feature that nDPI provides is the study of the entropy of the communication. So in essence, the entropy is a number that identifies how the byte payload are distributed. So let's say the higher is the entropy, the more distributed are the bytes across a certain range. So the way nDPI computes it is the following. So every byte is from 0 to 255. So we take the first few packets, usually up to 32, and we take every single byte of the payload, and we go into this long vector and increase by 1 the bucket that contains the byte X. So at the end, we compute the entropy. And what we can realize that byte entropy is not useful for understanding 100% the type of data being exchanged, but it is good with some protocols to understand whether the information exchanged is not the one we expect. Next slide, please. This is because there are some typical entropy values for protocols. So for example, Skype has a byte entropy value of about 6.5. Okay, so if you see this value, okay, you say, okay, this is Skype because it looks like Skype, but also from the value, it looks Skype. So the entropy says, okay, we can confirm that. But if you want to use it for TLS, for instance, or for SCP, so in this case, a secure copy over SSH, the use of entropy is good only to understand the boundaries, upper and lower boundaries, but not to really understand or to speculate about the type of information being exchanged. Let's make an example. These are statistics taken exchanging various types of PDF files and PNG or text files between two hosts. And the size of the PDF, the content, so in terms of pictures, images, is very different. So we have taken various different types of files. And as you can see, with PDF, we have an entropy value of about 6.4. That looks good, somehow stable. But if we take other type of information, such as a PNG, so an image or a text file, we have two different values, so around 7, that are very close. So it's hard to say if somebody is copying over SSH an image or a text file. But for instance, we can say if PDF, is different from other type of files. And this is particularly important if you have some predictable type of information. So let's say if you have an IoT device, or if you have a server that is doing continuous backup, or if somebody that is SSH to the machine, to expect always some sort of entropy, standard entropy for that communication. So entropy is not good in general for fingerprinting traffic, but it's good for this type of purpose. Next slide, please. So if we want to do something more sophisticated, then we have to understand a little bit more the behavior of the traffic. So this is one example. This is TrickBot, but it's one popular, unfortunately, malware. As you can see, these are information that are reported through ntop tools, through nDPI. So you see that in blue, we have the packet sequence. So you have positive value when the first case 95 means that the client has sent to the server a packet 95 bytes long. And the other server has replied, that has a minus value, with a packet of 19 bytes. And then the client has sent another packet of 134 and the reply of 59. So as you can see, these patterns are very similar, okay? Because there are some little changes, but they are more or less the same. And as you can see, if we can divide the packet length or the time distribution into bins, so a set of ranges that where the packet can be accommodated, they look very similar. So you can see the orange or the red are very, very similar. And in this case, also the entropy is the same. So this is an example that I wanted to show you to show that you can characterize the traffic even without decoding, simply looking at the outside. So if you're able to spot, let's say, a machine that's been compromised, you can find similarities in other type of traffic, and you can find similarities also across different machines. So this is the important thing that I think we have to do, is particular for malware analysis, if we want to find similarities in traffic, even if we are unable to understand the nature of the traffic. Next slide, please. So now going to the last part of the presentation, that is probably the one that is most relevant for you, is about the encryption of TLS. So up to 1.3, there was only one message in clear text called client hello. The client hello, in essence, the client speaks with the server and says, I want to talk with this SNI, with this server, and these are the options that I want to use. So let's say with ALPN, for instance, that is one extension I mentioned before, the client is telling the server that I plan to use, let's say, HTTP 2.0. Unfortunately, this is being let's say it's under being reviewed, because inside the TLS in 2019, there have been an extension called ESNI, Encrypted Server Name Indication, that in essence is sending the SNI encrypted. So instead of sending the usual name, so maps.google.com, so in this case, this information is sent encrypted. How? The client is talking with the DNS, and through DNS it is reading the public key of the server. So it is encrypting the SNI with this public key and plus some extra information. So in essence, we are unable to see the SNI in clear. So it is no longer possible, to say that we are now talking with Google Maps, and this is becoming a problem. Next slide, please. And the problem is becoming even more challenging because there is a new draft called ECO, okay, that is proposing in essence not just to encrypt the SNI, like I've shown you before, but to encrypt the whole client hello. So therefore, this will prevent fingerprints such as JA3 from working. We are not able to see with LPN if the idea of this TLS communication is to exchange hypertext data or to do, let's say, a VPN. And therefore, this is creating a lot of problem. Also because in addition to this, one of the things that this ESNI and ECO are using is secure DNS. So it means that we are not longer able to see DNS traffic in clear. So therefore, all this communication is encrypted. So we cannot speculate, for instance, recreating a DNS IP to name cache, what type of service is contact. But unfortunately, this is no longer possible if all these three techniques will be used simultaneously. Next slide, please. So what are the implications of visibility? Okay, first of all, we have a problem with TLS fingerprinting because most of them will not work. Only a few of them, the one I showed you before on 3 slides ago, are still working. So the beans, the entropy, they will work, but we are not able to see anymore the SNI we're talking to. One option is to block this type of communication. There are some proxies, for instance, or there are some operators that can block, let's say, this type of protocol. So in case a TLS extension is sent out with this extension, it can be blocked. Or otherwise, another option is to, let's say, block DOH or DOT, so that, let's say, the operator can provide those type of servers similar to the DNS today. But in case somebody wants to use one DOH service, for instance, provided by Cloudflare and not by the operator itself, it can block it. This is another possibility. Fortunately for major companies such as, let's say, Microsoft, Facebook, and others, they are publishing the list of IP addresses and ports used by certain protocols. So it is still possible to have, in this type of, in this special case, visibility of the services, because the big players are interested, at least most of them are interested to report this information to make sure that their services are working and the firewalls are properly configured. But this is no longer the case for everybody, unfortunately. Next slide, please. So for instance, today there is Firefox that with Cloudflare is trying to let's say to encrypt everything, and even though they are not using ECO, they are using encrypted SNI, and this is somehow creating some problem in terms of visibility. Fortunately for malware, I don't see a big problem for the next for the near future, let's say, because most malware communication are still using, all the TLS 1.1. We are not still using HTTP. So somehow this is it's a minor problem, I would say. And there is also the possibility of using clear text DNS. But the idea of those companies such as Mozilla is to prevent any information leak. So they are suggesting clearly to move to DOH, because otherwise Firefox will not use the encrypted SNI. Okay, then the next slide you will see the URL of nDPI, and this is basically all. I'm here to answer questions.
Perfect. Thank you, Luca, for a very exhaustive, if rapid run through, which I think threw up some interesting points. So hopefully that's prompted some questions from those of us on the call. Who would like to jump in first with a question? And you might be on mute, so do bear that in mind. If you're talking, give people a chance to think. There's quite a lot to absorb.
I had a question about analyzing flows. So you mentioned you only look at the start of the flow, the first few packets, which makes sense because that's what every other platform does as well. My question is, how does that interact with TLS session resumption? So, as I understand, if you resume an encrypted session between client and server because they've remembered the keys from the last time, the new session, I guess, somehow reuses that encrypted state. So, in that situation, are you able to still analyze it, or do you treat it differently?
Well, let's say nDPI has a goal to analyze the first few packets of a communication. So in this case, when nDPI has reported the protocol, I think we are good. So it is mostly the application that is sitting on top of it to do this type of dissection. So as far as I remember, if you resume a session, still some information is present in the initial part of the communication, so in the handshake. So if I remember correctly, you should be able to see, information such as those I show you in this presentation. But the idea of nDPI is just to monitor the first few packets. It's mostly an application problem, let's say.
Okay, so yeah, might be worth some testing then, just to see how it acts. Okay, thanks.
Okay, thanks, Chris. Who else has a question for Luca?
I do. This is John Todd from Quad9. Have you done any real-world analysis actually looking at DOH to determine if it is able to be easily categorized, based on your flow analysis?
What we have done is this. Okay, inside nDPI we support the most popular public servers, and what we can do is that we have started some studies where we want to characterize the traffic base, let's say on packet line, on let's say the time between a request and response, and this type of activities to understand if this looks like a DNS, a DOH, let's say over TLS. I don't have results. Okay, so we are still running some tests. Let's say that many times we are able to find the correct answer, but sometimes based on also on the traffic, it's hard to say because it depends also who is using that. So if there is one client that is using that session, okay, it's more predictable. But if you have, let's say, a DOH server or a proxy, so that local clients from a network are sending traffic to this proxy, and this one is speaking in DOH with let's say a provider, this is more complicated because the traffic is less predictable. So we are still making experiments. I don't have an answer. We have some positive results, but at the same time, I don't have a yes answer. valid 100%. I believe that probably with some more classification, we are able to detect it with machine learning, with let's say longer observation of the traffic. We are able to determine that. But again, nDPI is usually focusing only on the initial few packets, and then it's the application that is sitting on top of it that should do that. So, for instance, even for the entropy or for the other type of communications, nDPI is providing the library for doing that, is computing it on the initial payload bytes. But if you want to monitor over the time the entropy, that is another good indication, for instance, for encrypted communication, this is something that nDPI will not do. So it's the application on top of it that has to do that. However, we plan to complete this test as soon as we have more examples of DOH, because at the moment we are just using browsers, or we are using those services like the one provided by systemd to provide to a set of host DOH. So we're still making experiments in this.
Paul, do you want to jump on?
Sorry to be late. Thank you, Luca. This has been fascinating.
Thank you.
I note that DOH is not, probably will not remain in its current form. I have heard that they will be adding padding in order to frustrate this type of traffic categorization, for example. And so I look forward to your work on that. I wonder though, have you looked at all at the QUIC protocol to see if it can also be characterized in order to measure it?
Yes, with QUIC at the moment, we don't have many problems, because even though Google is changing, from release to release, the format, we are able to detect the SNI is clear, is one packet is doable. So QUIC at the moment is more under control than TLS. However, going back to DOH, DOT, I mean, we're still making experiments, but I believe that over the time, TLS and QUIC will become their protocols. So, for instance, at the moment for malware detection in LAN in particular, or for crypto lockers, okay, the Windows file sharing was SMB was perfect because it's a protocol in clear test. Now Microsoft has introduced, or at least as experiment has introduced SMB over QUIC. So, I mean, even though we are able to decode QUIC, at least the initial packet, so to understand and characterize it, the problem is to characterize the content. So in a way, this is similar to the DOH question asked before. So how to characterize that? At the moment, we are looking at packet timing, at packet length, packet distribution, packet trains, and at let's say entropy. So the way the information is exchanged. But I mean, QUIC or TLS have the same problem, unfortunately, for this type of protocol. So we are still struggling. So I hope to release some results soon, but it's not really simple, because it depends on the use case. In case of SMB, for instance, it's simple to do SMB over QUIC because it's a one-to-one communication. But in case of DOH, it's more complicated depending on the installation, on the deployment. This is the problem.
Okay. Thanks, Paul. Ralph, if you're on mute, if you want to come off mute, I think you've got a question.
Yeah, one question, one remark. So is my understanding correct that most of the categorization that you are currently doing for DOH is based on the sort of service provider that is offering the DOH service? And the remark was that, I mean, padding already exists within DNS, and as such, I know at least of a couple of implementations that also add the padding when they send stuff out via DOT or DOH. So that already is there, and that probably has some implications on the work you're doing.
Well, let's say at the moment we are trying to characterize the traffic, like I've said, based on the bucket plan and the various features I mentioned before, and about entropy. I don't consider padding very relevant for this analysis because, like I've said, with TLS, padding, unless it's huge, is not changing much. Okay, the main problem is to understand, also to give some sort of accuracy, okay, on the detection, because we have noticed that based on the traffic, based on the usage of a certain communication, how can you say if this is, let's say, a VPN or DOH? It's hard to say, because even let's take a simpler protocol like SSH. So if I want to exchange a file, okay, so a copy, it's very simple. I know the direction. I know that the packet tend to be as big as possible. But if you use it as interactive shell, it's more complicated. Okay, or at least you can say this is SSH, looks like SSH, and it's like that. And the same for DOH. So if you exchange some packet from time to time because you want to resolve one domain here or there, it's fine. But if you're using in a totally different context for, let's say, for a network, even though the protocol is the same, the fingerprint and the rest is a little bit different. And also the timing between packets and sites. So this is where the challenge is at the moment.
Okay, anyone else want to come in with a question for Luca?
I have a very simple question. Are you supporting both IPv4 and IPv6 on this? And is there any significant difference between the two in terms of the capabilities?
Yes, we support both. No, there are no changes to say.
Good question, thanks, Ian. Right, last chance for a question if anyone has a burning one before we move on. Taking silence as not. In which case, Luca, that was extremely helpful. Thank you for pulling that together at short notice. I think you've given plenty of people food for thought in terms of your findings today. And it looks like there's a fair amount more work to do, given the changing standards that you're dealing with. It's a work that's never finished, so thank you. That's very much appreciated. For everybody else's benefit, I'll resend a link to Luca's blog with the notes of the meeting as well as the slides, so you've got those to hand. But I think that was well worth spending more time than you had at the RIPE meeting. I think that made it much more.
Sure. Probably at the next RIPE meeting, that's supposed to be in Milan, so close. Oh. I will show up.
Fantastic.
Thank you. Thank you for inviting me.
Thank you.
Bye-bye.
Bye. Right. Okay. So, given the time, we've run over a little, but I had allowed for that because I thought it was a fairly complex subject and there could be some questions. So that will bring us straight on to any other business. So, can I just poll people to see if there's anything that you would like to bring up whilst we're on the call together? Ralph?
Just to mention, as I think sent you via email, there's a virtual DNS org on June 9th. People might be interested in.
Yeah, and I'll include the details for that, Ralph, also with the notes as well. So thank you for flagging that. Whilst we're talking about meetings, also next week is Eurodig, which runs on Thursday, Friday, I think, next week. So if you want to attend that, if you register by the 9th, then you'll be able to access it using Zoom with proper access to the various sessions. After the 9th, I think you can still join, but you'll be limited just to the live stream. So be in sort of passive viewing only, rather than be able to ask questions and fully participate in the conversation in the workshops. So if you are thinking of joining any of the sessions, please register by the 9th. And I should commend to you a number of the sessions, not least of which the workshop 3 on encrypted DNS, which takes place on the first morning. Workshop 5 on internet standard setting and whether it should include input from stakeholders other than just the tech community in setting standards. There's a good plenary session, plenary 2, on digital sovereignty, and also workshop 11 on the take-up of standards, amongst many other topics. So if you do have time next week, well worth registering. It doesn't cost anything other than your time, but do register by the 9th if you want to take part properly in the discussion, rather than just viewing it as a live stream.
Andrew, glad here. I got one thing to share. So now that I'm getting over being sick, not with COVID, something else, guys. The work that the Eddie group did a couple weeks ago, where we brought people together working some use cases. My goal is I'll get that posted up to the GitHub and send a note out to Eddie list later today. And one note, we last week we had a glitch with, ironically, with the signing keys for the encrypted DNS -org domain, which is behind the mailing list. And so some people may have received some automated unsubscribe notices from the list. Those were in error. We weren't kicking anybody off. I've tried to go through and find everybody and re-add you. But FYI, if you're not getting any mail, that's probably what's going on. We fixed the signing thing. Crypto is great when it works, and when it doesn't work, things barf badly. So FYI, everybody.
Brilliant. Yeah, I think moral of that is you can't afford time off sick, Glenn. Clearly, it all goes wrong when you're not there.
No. This was the crypto signing was not me involved. That's a whole different team. Good guys, but I can't take credit for that one.
Fair enough. Okay. One other thing, just to give you a heads up, or so 2 other things. We will have a session on DOE fingerprinting coming up with one of Brett Carr's colleagues from Nominet, which he mentioned on the call the week before last. So that's scheduled for the 15th. So for those of you that are interested in that, I'll update the agenda next week, but just to give you advanced notice of that, so you're aware it's coming up. And we're going to discuss next week the proposed certified resolver policy, if I can say it properly, for European resolvers, which a number of you have input comments to the draft for that, but we actually spend some time next week talking about that. So again, I'll give you a heads up on that. There should be a bit more interest, in particular to your policy people, where appropriate. Okay, last chance for any last comments, should anyone have them. Otherwise, I hope you all found that session useful. Thank you for Jim for suggesting it. I think that was most helpful from Luca. Expect the notes out the next couple of days, and have a great week, everyone. Thanks for your time.